Students, this is the next lecture, the third lecture for your Wednesday, July the 15th class. We're working on chapter 11, and we left off right here on discharge. So, when you're thinking about rivers or streams, you always want to think about one of the things we monitor is the discharge of the river. What does discharge mean? Well, discharge means the amount of water that passes by a spot on that river channel per unit time. What does that mean? Well, discharge in the United States is measured in cubic feet per unit time. So it could be cubic feet per second, or cubic feet per minute, or cubic feet per hour. The rest of the world measures it in cubic meters per unit time. So it would be in cubic meters per second, cubic meters per minute, or cubic meters per hour. In the United States, so let me draw you a picture here. So here's your meandering stream. Let's say it's flowing south this way. And the U.S. Army Corps of Engineers sets up things called gauging stations up and down the length of all the major rivers in the United States. The U.S. Army Corps of Engineers sets up gauging stations, and these gauging stations are used to measure discharge along any point. Let's say this is the Mississippi. Well, the Mississippi begins up here in Minnesota. Yeah, you betcha. It's over here, don't you know, up in Minnesota. And then it goes all the way down here to Baton Rouge, New Orleans. And so we have a whole bunch of gauging stations going down the Mississippi. Later on, I might as well just tell you now that the place where the river begins is called the headwaters of the river. The headwaters of the river. So the headwaters of the Mississippi is up in Minnesota. And where the river ends, that's called the mouth of the river. So the headwaters up in Minnesota, and the mouth is down here in New Orleans, where the Mississippi flows into the Gulf of Mexico. Anyway, we have these gauging stations going all the way from the headwaters down to the mouth. Let me show you what the gauging stations look like, so you can see what a surface water hydrologist does for a job, for his paycheck or her paycheck. Let's see. USACOE, U.S. Army Corps of Engineers. U.S. Corps of Engineers Stream Gauging Station. Okay. See this? I don't know if you've ever noticed these little huts that they have here along the Tennessee River or the Clinch River or whatever. Inside of there is a device that records how much water is passing by this spot on the river. There's a little propeller thing, and the faster the propeller goes, the more the discharge. So discharge is how much water passes by a spot per unit time. Why do we want to measure discharge? Why does the Corps of Engineers spend billions of dollars of our taxpayers' money to measure discharge along these rivers? The reason why we do it is so we can prepare for floods. Floods are the kill more people than earthquakes, volcanoes, and landslides combined, and they're a big problem. So, in order to warn the public and to prepare for a flood, we want to measure discharge, and we plot our discharge data on a hydrograph. What's a hydrograph? It's kind of slow here. Okay, this shows you. Uh, well, let me see. Yeah. Okay, this shows you a discharge versus time diagram. So, 1,200 hours. That's and then 1 o'clock, 2 o'clock, etc. And and so this is time on the x-axis, and what you see here is discharge over here, and it's metric here, 50 cubic meters per second. So 10 cubic meters per second up to 50 cubic meters per second. So usually your hydrograph is going to look like this. Ah, Holy Mother of God. Let me do it again. Usually your so I'm going to draw your hydrograph. Your hydrograph is always represented by the capital can't talk today. The capital letter Q, discharge, and let's say it's in cubic feet per minute, or cubic meters if you want to. And then we have time here on the x-axis. So this is noon, this is 1 p.m., 2 p.m., so this would be 6 p.m., and this would be midnight, etc. So usually your hydrograph is going to look like this. The discharge isn't going to change much during the day. But here you can see that all of a sudden your discharge is going up. More water is flowing past that spot along that river. What's going on here? Well, they also put precipitation here on, so they also measure precipitation here in millimeters. You can put that in inches if you want to, but and that's what this gray histogram represents. So you get more and more rainfall, and then the rainfall peters off. Well, if it rains more, you're going to get more discharge, right? More water is going to flow through that river. So if it rains a lot, your discharge is going to keep going up. It's going to go up. It's going to go up. And what happens? It reaches this peak. This is called the peak discharge. And what's happening is, why is discharge going down after this? That's because the river overtopped its banks. It went over the levees, and the discharge was released into the floodplain. So here you can see peak rainfall, and here you can see peak discharge. There's a relationship here, and there's also amount of time that passes between peak rainfall and peak discharge, and that's called the lag time. So the U.S. Army Corps of Engineers, they're making these hydrographs 24/7, and if you're a hydrologist working for the U.S. Army Corps of Engineers, you get this data on your cell phone every day on your computer, and you can watch your discharge versus time, your hydrograph, discharge versus time diagram, your hydrograph. And most of the time, you're going to just get something like this because there's no rain. Discharge versus time. But if you get rain, Then your discharge, if it rains a lot, your discharge is going to go up and it's going to hit a peak. And then it's going to hit that peak discharge right here. And then it's going to, once the river overtops its banks, then the discharge will go down because the discharge water is being is leaving the channel and going onto the floodplain. And as I mentioned before, you can also plot precipitation here. So when it rains, you're going to get peak rainfall right here. You're going to get peak discharge here. And the amount of time that passes between maximum rainfall and peak discharge is called the lag time. Okay, so there's your hydrograph there. And now you know what a hydrograph looks like during a flood. And we always plot precipitation on the y-axis, and we also put discharge on the y-axis, and we monitor how discharge changes during the day and also how much rainfall we have over here. To understand this better, let's compare a hydrograph, discharge versus time, for a city, let's say for Knoxville, for example, versus discharge, which are versus time. In other words, we're going to compare the hydrograph for a city versus a rural area out in the country, such as in I don't know, just pick a place out in the country. And remember, we're also going to plot precipitation. So first, let's say it rains. It rains a little, and then it rains more, and then it hits your peak rainfall right here, like this. Let's say for to make it to compare the how floods are different in the city and the country, let's make everything the same. You have the same exact rainfall in both places. Okay, and it happens at the same time. How is the discharge going to be different? How's your hydrograph going to be different from the city versus the country? Well, for a city, your hydrograph is going to look like this. There's your peak discharge there. Whereas for the country, out in the rural area, it's going to look more like this. Comparing these two hydrographs, which one has the higher peak discharge, the city or the country? The city has a bigger peak discharge, right? A stream flowing through Knoxville will have a higher peak discharge when it rains. Out in the country, you're going to have a smaller peak discharge. Which has a longer lag time? A creek flowing through a city or a creek flowing through a rural area? Well, lag time is the amount of time that passes between peak precipitation and peak discharge. So the lag time for a flood that occurs in the city will be shorter than that for the country, right? Bottom line is, when you compare these two hydrographs, that of the city versus the country, you get a higher peak discharge for the city and a shorter lag time, don't you? Let's put that in layman's terms that everyone can understand. When it rains in the city, the floods hit are stronger and they hit faster, don't they? Why is it that floods are more powerful with the same amount of rain in the city and the floods hit you faster after the rain? Why do you think that is? Well, when it rains in the city, there's more concrete and asphalt, isn't there? So the water can't infiltrate into the water, so it runs straight off. So in the country, you have more dirt roads and more less concrete and asphalt, so the ground can absorb the precipitation, right? Therefore, the floods aren't going to hit as hard in the rural area. They're going to It's going to take a longer time before after it rains before you have the flood because the ground is absorbing that infiltrating precipitation. Don't forget, please, that discharge is the amount of water that passes by a spot along a river per unit time, and it's measured in units such as cubic feet per second or cubic meters per second. Next thing we want to learn about is stream gradient. What is stream gradient? Well, let's draw a picture to show you that. A river flows downhill, doesn't it? Gravity carries water downhill, so um, it's going to go downhill, right? So let's say this is the bottom of the riverbed right here. The water is going to flow downhill. So this is the bottom of your river channel here, and this is the water flowing downhill. The steeper the river channel is, first of all, do you think that if the river channel is steeper, do you think that the water is going to flow faster? Yes. So stream velocity is going to increase with gradient. What is gradient then? Gradient is a measure of how steep the slope is of the riverbed. You already learned about that back in high school. It's called slope, right? That's a steep slope. That's a gentle slope. Slope. Remember back in high school how your math teacher would talk about slope? It's equal to rise over run. Remember, your geometry teacher probably told you about that. So let's say that this is our slope here, this line here. This is our slope. This is the rise. And this is the run. In the United States, we usually measure this, instead of saying slope, though, in geology we call it gradient. And gradient is simply the slope of the riverbed. Which is equal to rise over run. So uh, the rise is the change in elevation from one place to another on along the river, and it's measured in feet. The run is the distance between those 2 points along a river, and that's measured in miles. So stream gradient is measured in feet over miles. let's say, for example, we have a topographic map, and we have um, the following contour lines, like like this. So this is your 200-foot line, and then like this, and this is your 180-foot contour line, and like that, that's your 140-foot contour line. I'm sorry, it should be 160, but your contour interval is 20 feet. And then we'll do one more like that, and that's 140 feet. So this is for a contour map with a 20-foot contour interval. Now let's put our stream in here, and we'll just, here's our stream, and we'll call this stream Jones Creek, because I have I don't have too much of imagination this morning. Call it Jones Creek. Okay, Jones Creek is right here. First of all, notice that the contour lines V, or they point upstream. So right here on the in the river, you're 200 feet above sea level. Right here, you're 180 feet above sea level. Down here, you're at 160 feet above sea level. Don't forget that north is always up on your maps. Which way is Jones Creek flowing? I'll give you 10 seconds to think about it. Water flows downhill. Contour lines point upstream. So this is upstream, and so the Jones Creek is going to flow to the southwest, right? Now let's figure the gradient of Jones Creek. Let's figure out the gradient of Jones Creek. How are we going to do that? Well, gradient is equal to rise over run. Let's say that this distance here on your map is 1 mile. So that's 1 mile. So if I were to walk from here to here, that'd be about a mile, right? Okay, to figure out the gradient of the stream gradient, we need to find two contour lines that cross the creek. Well, you could find two. It's very easy. Here's one, and we'll call this point A. Here's another place where the contour lines cross the creek, and we'll call that point B. So we're going to measure the stream gradient by determining the rise over run from A to B along your stream. What's the rise from A to B? What's the change in elevation from A to B? Well, here you're 200 feet above sea level. Here you're 180 feet above sea level. So your rise would be what? 20 feet. That would be the rise from point A to point B, right? What would be the run from here to here? Well, isn't that exactly the same as this here? So your run in this case would be 1 mile. So what's your stream gradient for Jones Creek? Your answer would be 20 feet per mile. See how that works? So stream gradient is how steep is the stream bed. Let me ask you a question. If a river has a steeper gradient, do you expect stream velocity, the velocity of the water, to be higher or lower? Higher, right? If it's steeper, then more water is going to flow down faster. If this is the stream bed and it's very steep, then the water is going to flow down faster. On the other hand, if it's a gentle stream bed, the water's going to flow down slower. You think that if the stream gradient is higher, the discharge should be higher? You think more water would pass by a spot per unit time if you had a steeper gradient, a steeper riverbed slope? Sure. So there's a relationship here. And that is, the steeper the gradient is, you would expect a higher stream velocity and a higher stream gradient, right? I mean, the steeper the stream gradient is, the higher the discharge and the higher the stream velocity. I hope you're following with me here. If you don't, listen to it again. But I'm going to show you why life is not so simple, why it's not that easy. Let's say we have a stream and it's flowing like this, like the Mississippi, for example, which flows south, right? Or southeast in this picture, okay? So let's say we had a gauging station up here in Minnesota, where the Mississippi River begins, the headwaters up in Minnesota. And let's say we put another gauging station down here in New Orleans. The stream gradient is much higher up here in Minnesota because you have those very steep canyons where water's dribbling in, and that's where the Mississippi begins. But by the time you get to New Orleans, the stream gradient is almost zero. It's almost flat. Then why is it that the discharge here at this hydrograph at New Orleans, you get higher numbers than you get up here in Minnesota? Because we just said if stream gradient is steeper, you should have a greater discharge. The reason why is because as the Mississippi River flows a couple thousand miles from Minnesota to New Orleans, you have other rivers that are feeding into the Mississippi, like the Arkansas River and the White River, and the Tennessee River. So more and more water is flowing into the Mississippi. So by the time you reach New Orleans, and here's the Gulf of Mexico over here, the Gulf of Mexico, you have very high discharges as the water flows into the ocean. So you just can't make the assumption that the steeper the gradient is, the higher the discharge. But what you can say is the steeper the gradient, the faster the water moves. The greater the stream velocity. Okay, we're going to call it quits for now, and I'm going to eat lunch, and I'm going to do another video later.